Dear students, let us start with derivation of elemental stiffness matrix for 1D bar element. In order to derive elemental stiffness matrix, we have two methods. One is direct method, the one more is strain energy method. Now let us see the derivation of elemental stiffness matrix by using the direct method approach. Let us consider a bar of uniform cross-sectional area A having Young's modulus E subjected to the force F having a length of L. Now represent this bar element in finite element model. It is modeled by two noded element. So at node 1, let us assume that the displacement is U1. At node 2, the displacement is U2. Also assume that at node 1, it is subjected to a force of P1. At node 2, it is subjected to a force of P2. We know that the polynomial equation for two-noded bar element, which is written as U is equals to A0 plus A1x, which I already explained in module 1. Now, I will rewrite this equation in matrix form. I will remove the constants A0 and A1. When you remove the constants, we'll get 1 comma x. 1 comma x into A0 and A1, called as equation number 1. Now, applying boundary conditions at node 1, the value of x, it will be 0. The displacement at node 1, which is defined as u1. Now you substitute these two conditions into the polynomial equation. So u it becomes u1, x it becomes 0. So we'll get u1 which is equals to a0. Again you apply boundary condition at free end. At free end, the value of x is L. The displacement at node 2 is u2. So u is equals to u2, which implies u2 is equals to a0 plus a1 L. u2 equals a0 plus a1 L. Now these two equations I will write in matrix form u1 comma u2, which is equals to, so here we have only a0, a1 it is not there, so it is a 0. So when you remove this a0, so we'll get 1, the second term is 0. In this equation, when you remove a0 and a1, here you will get 1 and L, 1 comma L into a0 and a1. In equation 1, we need the matrix value a0 and a1. It is a constant. So I will send this matrix towards right hand side. So left hand side, a0 a1, which is equals to inverse of the matrix into u1 and u2, called as equation number 2. Now you substitute the equation 2 into equation 1. So therefore the displacement model u, which is equals to 1 comma x into a0 and a1. a0 and a1 is this much, 1 0 1 L inverse u1 and u2. You find out the inverse of this. When you find out the inverse of this, the value of that, it will be 1 comma 1 divided by L in the bracket L0 minus 1 1 into u1 and u2. Now you expand this. When you expand this, so 1 into 1 by L into L. So you'll get 1 x into 1 by L into minus 1, you'll get minus x by L. So you'll get 1 minus x by L, one term. Again the second term, 1 into 1 by L into 0 is 0. X into 1 by L into 1, it is x by L. So I'll get 1 minus x by L dot x by L into u1 and u2. You got the displacement equation. Now we know that strain along x-axis, which is given as epsilon x, which is equals to epsilon, which is nothing but dou u by dou x. Now you differentiate this with respect to x. So when you differentiate this, so differentiation of 1 is 0 minus differentiation of x by L, it is minus 1 by L, minus 1 by L, comma. Again differentiation of x by L is 1 by L, 1 by L into U1 and U2. When you remove 1 by L outside, so you'll get 1 by L minus 1 comma 1. So 1 by L in the bracket minus 1 1, which is nothing but the strain displacement matrix, which is represented by B, which I derived in the previous video. So strain, which is nothing but B into U or B into Q. From Moore's law, stress is nothing but Young's modulus into strain. So sigma, which is nothing but EB Q, or sigma equals E into, so B is nothing but minus 1 by L, comma 1 by L into U1, U2. From figure, we can observe that the force P1, it will cause us a compressive stress, and the force P2, it will cause us tensile stress. So P1, it will cause us a compressive stress. P2, it will cause us a tensile stress. By principle of superposition, at node 1, we can write stress as sigma is equals to load by area. So load is P1, which is a compressive. So I have taken it as a negative value. So therefore, P1, which is equals to minus sigma into A. At node 2, again sigma is nothing but load by area. So load is P2 divided by uniform cross-section area A, which implies P2 is equals to sigma into A. Now I will represent these two in matrix form. So P1, P2, which is equals to sigma A, I will remove outside. So I'll get minus 1, 1. Now you substitute the value of stress in this equation. So we know stress is this much. Sigma is equals to E into minus 1 by L, comma 1 by L into U1, U2. So therefore P1 by P2, P1, P2, which is equals to A minus 1, 1 into the value of this E into minus 1 by L, comma 1 by L into U1, U2. Now I will rearrange this. So P1, P2, AE. Again in the matrix, I will remove 1 by L. So we'll get L. Now you multiply two matrices, minus 1, 1 in the bracket, minus 1, comma 1. So when you multiply this, minus 1 into minus 1, it becomes plus 1. Minus 1 into 1, it becomes minus 1. Again 1 into minus 1, it becomes minus 1. 1 into 1, it becomes 1 into U1, U2. Now this term, I will represent it as a K. So therefore, the P1 and P2 are the forces at two nodes. It is represented by a load vector P. This term I will represent it as a K. U1 and U2 are nodal displacements. I will represent it as a global nodal load displacement vector. It has a U. So this equation we will call it as a displacement relation, where the value of K, which is given as AE by L into 1 minus 1 minus 1, 1. So this is the elemental stiffness matrix for 1D bore element by direct approach method. Now let us start with the one more method. So it is a strain energy method. So consider again the bar element having two nodes. Let the displacement at node 1 is Q1, displacement at node 2 is Q2. It is represented in both Cartesian coordinates as well as natural coordinate system. So let node 1 is located distance of x1 from the origin. Node 2 is located distance of x2 from the origin. In natural coordinate system, the value of zeta at node 1 is minus 1. The value of zeta at node 2 is plus 1. We know that strain energy for a 3D body, which is given by strain energy equals half times of integral of volume sigma transpose epsilon into dV. This we derived in module 1. For 1D bar element, strain energy which is equals to half times of Replace volume integral to the line integral. So integral of length of the element sigma transpose epsilon. Replace volume by A into dx for 1D bar. Therefore, strain energy equals half times of integral. So sigma is nothing but EBQ, which we derived in the strain displacement matrix transpose. So again, strain is nothing but B into Q into A into dx, which is equals to half times of line integral. E is a constant, so transpose is not applicable. So B transpose into Q transpose, B transpose into Q transpose into E, B into Q into A into dx. Now it is in Cartesian coordinate system. So for simplification, I will replace the Cartesian coordinate system to natural coordinate system. So replace the dx in terms of d zeta. We know that relation between natural coordinate system and Cartesian coordinate system, which is given as zeta is equals to 2 times of x minus x1 by x2 minus x1 minus 1. You differentiate this with respect to x. So I'll get 2 divided by x2 minus x1. x2 minus x1 is nothing but the length of the element. So 2 by L, which implies so dx, which is equals to Le by 2 into d zeta. Now you substitute this value of dx into this equation. Therefore, strain energy equals half times of, I will remove Q transpose outside in the brackets. So when use instead of dx as d zeta, so the value of d zeta, it always lies between minus 1 to plus 1. Therefore, the integral minus 1 to plus 1 b transpose into E b a dx. dx is La by 2 into d zeta in the bracket Q. I will arrange in this fashion. Therefore, strain energy equals half times of Q transpose. This entire term, I will call it as a Ke into Q, where this Ke is the elemental stiffness matrix, which is given as integration of minus 1 to plus 1 B transpose, B transpose E B A La by 2 into d zeta by 2. So E is constant, A is constant, Le is constant, so divided by 2. So which is equals to EA Le by 2 integral of minus 1 to plus 1 B transpose B into d zeta. Again, we know that the strain displacement matrix B is 1 by Le minus 1, 1 and B transpose is 1 by Le minus 1, 1. So substituting this into this equation, so Ke is equals to Ea into Le by 2 integral of minus 1 to plus 1 1 by Le minus 1 1 into 1 by Le minus 1 1 into d zeta. So Ea by Le, so 2 by Le, I will remove this Le towards outside, so it becomes Le minus 1 1 into minus 1 1. You multiply these two matrices, minus 1 into minus 1 it becomes plus 1, minus 1 into 1 it becomes minus 1, 1 into minus 1 minus 1, 1 into 1 it is plus 1. Integral of remaining term is d zeta, minus 1 to plus 1 d zeta. Now you integrate this d zeta. When you integrate d zeta it becomes zeta minus 1 to plus 1. Apply the limits. When you apply the limits, you will get 1 minus of minus 1. So you will get 2. So you cancel that 2 and this 2. So finally we will get K is equals to Ea by Le 1 minus 1 minus 1 1. So this is what elemental stiffness matrix for 1D bar element by using strain energy method. Once we derive elemental stiffness matrix, so it will have some properties. So properties of stiffness matrix. The first property is if there are n number of nodes, then the global stiffness matrix, it will be n cross n, provided element is a 1D and 1 degree of freedom at each node. That means if a element is consisting of n number of nodes, then the stiffness matrix will be n cross n. For example, in our case, I have taken 1D bar element. It consisting of two nodes. So n it becomes 2. So the stiffness matrix it will be 2 cross 2. You can cross check it over here. So it is a 2 cross 2 matrix. That is the first property of stiffness matrix. The stiffness matrix is a symmetric matrix. Symmetric matrix means so the elements above the principal diagonal, above and below the terms are always symmetric. That is the second property. The third property is the determinant of the matrix will be always 0. When you expand this, the matrix, when you find out determinant, so it will be always equals to 0. And the last property is the diagonal elements are always positive. That is, the principal diagonal elements, it will be always, it consisting of positive values. That is non-zero positive values.